Imagine the universe as a flat, modular grid. Clean tiles, locked edge to edge. Now drop in a star, now drop in a galaxy. In quantum physics theory, that object doesn't have mass from birth. It gains mass only at the Higgs scale, and only in the places where it touches the grid. That Higgs scale mass is the anchor. It bites into the tile. It keeps the big stuff from skating around. So how stable are these anchors over time? 3 effects matter: coupling, indexing, bleed. First, coupling. The Higgs field permeates mass and sets the anchor's stiffness. Stronger coupling means tighter lock-in, less drift across tiles. Mechanical firmness, like a tripod on concrete instead of sand. As celestial bodies evolve, spin down, trade angular momentum, shed material, accrete material, the Higgs coupling locally recalibrates, preserving the anchor's bite without changing the grid's shape. Second, indexing. The grid is modular. It updates by re-indexing tiles, not by flexing space. When a system changes, say a galaxy bar forms, the grid doesn't curve, it relabels. Anchors hand off from one tile index to the next with phase continuity, the way a baton passes in a relay. Stability comes from that baton pass. No gaps, no overlaps, no tearing. Third, bleed, or rather, the lack of it. In this architecture, the expanse's zero-point energy lives in a separate domain. It governs acceleration and continuity fields, but it does not touch Higgs scale mass. That separation is the firewall. No mass-energy equivalence, no crosstalk between particle law and celestial gravity, no parasitic forces sneaking into the anchors. Over long timescales, what erodes anchors? Not the expanse, not particle jitters. The only stressor is resonance at the Higgs scale itself. If a body's rotation or tidal cycles match a grid harmonic, you can get anchor jitter. The fix is built in, the grid staggers its refresh cadence, desynchronizing just enough to break resonance while keeping phase lock. Now, slipstreaming. Because ships ride the expanse's continuity, they accelerate between tiles, like wind threading through lattice work. The anchors never feel it. The grid doesn't bend. Your craft glides. The cosmos stays pinned. Put it together. Higgs scale mass grips. The modular grid re-indexes without warping. Strict domain independence stops bleed. That's why celestial anchors stay stable. Not perfectly still, but perfectly locked across cosmic time. Galaxies spin too fast. That's the anomaly. Standard physics says dark matter. But what if some of that missing rotation lives in the way mass couples to an expanding space lattice? The expanse grid. Here's the idea in one breath. I separate a body's Higgs scale mass, the stuff that gives particles rest mass, from its total observed inertia, and ask if the expanding grid adds a tiny push or drag that tweaks rotation. To make that testable, I need predictions. First, the grid drag coefficient, lambda. If planets slipstream with the growing grid, then angular momentum won't match what mass alone predicts. Denser Higgs scale mass means tighter lock-in, so different grid friction. Second, expansion-induced torque. If new space modules keep popping in, they nudge celestial anchors. Regions with higher expansion flux should show subtly different rotation curves, older, quieter zones versus younger, high-flux ones. Third, the inertial delta. If I subtract Higgs anchor mass effects from total inertia, what's left, grid inertia, should correlate with expansion environment and not just with baryonic mass. Bundle that into a conceptual force, the grid coupling force, Fg. Think of it as proportional to 4 knobs. Lambda, the Higgs scale mass, mh. The local expansion rate the objects spin. Turn any knob, rotation shifts. Okay, so how do I falsify this? Compare rotation rates of similar mass exoplanets. At different cosmic latitudes or redshifts, does spin systematically drift with expansion flux? Map galaxy rotation curves against environmental age. Clusters in older regions versus filaments still stretching fast. Look for residuals, places where GR and visible mass predict one inertia, but observations say just a bit more. See if that bit tracks expansion, not matter. If those patterns don't show up, the idea fails. If they do, even faintly, we've got a new constant to measure, lambda, the grid coupling. That's the junction. Turn a cool structure into a risky, testable framework. I'm ready to write the proposal. Are you ready to poke holes in it?
Hi. Like a tree was grow, we expand and get bigger, finally petrified. This is our cycle.
In Higg's in biology, the body is affected by gravity. Drop a ball from up high, it falls to the ground. All bodies are ground, the planet's surface. When we grow from a baby, we experience gravity as a play line. Little older, we experience the theory of the gravity force. Finally, when grows somewhat old, we start experiencing change. Our energies slow down, our bodies get heavier. Finally, we start experiencing difficulties. Our body, among main things, get heavier because we have grown our height. Again, our bodies slow down more so than before, and we experience excessive slower physically and gain more weight that gravity stresses on our bodies and our health. We are only human. We have a biological clock-like system about the length of time we exist. Elon Musk, if we can find out what causes this ending cycle on human anatomy, we might be able to change that future 3056.